Today I'm going to present a paper, a general framework for adversarial examples with objectives. Overall, this paper presents a model that can generate adversarial glasses that people can wear in physical world and defeat facial recognition softwares. The third model of this research is white box attack, which means the attacker have the model, the feature space, and all the weights. This is also a decision time attack, which means the attacker can poison the data and have to work on the decision type. There are two subtypes of this attack. One is called dodging, and the other is called impersonating. As we can see, the dodging attack on the column A is that when an attacker wears these glasses, the model will not recognize the attacker as a person of who he is. For example, if one is a famous person wearing this kind of dodging glasses, the facial recognition model will not able to recognize that guy is someone famous. The second type is called impersonating. For the column B and the column C, if the attacker wears this kind of glasses, the facial recognition model will recognize the attacker as someone else. As you can see, the recognition software will recognize the attacker on the top to someone on the bottom. The core system of this attack is called adversarial generative nets. This net is built on generative adversarial networks, which is the famous game. The AGN have two major parts that get trained during the training of the network. The first part is called a generator, and the second part is called a discriminator, as you can see here. For each iteration of training, there are two parts. The first part is marked by the blue arrows, and the second part is marked by the yellow arrows, and the red arrows and the red boxes. In each iteration, for the blue part, the generator takes a random sample from a latent space and try to generate eyeglasses out of it. And then it combines with the attacker's photo, then feeds the entire result to the target network. If it successfully fools the target network, the result is returned. Otherwise, using this loss function here, the generator is updated. The generator will be updated. So this loss function have two parts. The first part is this loss g, which is defined up here, and it's also used in another game function of the discriminator. So this part means that the discriminator will work upon the result returned by the generator, and the more likely the result of the generator is the same as the real result, which means the generator performs good, the discriminator will return a score that are closer to 1. So the generator is trying to lower this score so that the discriminator won't recognize it as a fake result generated by the generator. The second part is called loss F. Loss F is very similar to what we have talked before in the class, that how far away this generated result is from our targeted result. So for dodging, this loss F means how different is it from the original attack image. For impersonating, it's how different it is from the targeted image. So after updating the generator, the discriminator get updated by maximizing the gain function here. As you can see, the discriminator is trying to produce a score of how real an image is. For example, for x belongs to the data, which are real data, the discriminator is trying to maximize the score, so um, to let the scores approach to 1 as much as possible. And for this, and for the samples get by the generator, the discriminator is trying to lower the score. So 1 minus the lower score is get maximized. Overall, hopefully after iterations of training, the generator will be able to generate results that are close to the target, while the discriminator is used to constrain the generator so that the generator still generates results that are, we call it, imperceivable to human beings. And it worth noticing that the kappa parameter here balance the weight between the loss G and the loss F. So I want to have a recap of what we have talked about in class before, the LP norm optimization. So in this optimization, we constrain our algorithm by using an LP norm of imperceptibility. However, this approach is kind of heuristic, that we don't really use LP norm when we're really looking at things. So the AGN provide an alternative way to approximate the imperceptibility by using the detector, which tries to kind of differentiate the generated result and the real result. It works, and it's also changed the misclassification function a little bit to account the changes. To train such network, the author provide a method of pre-training. So we want the generator to generate a result that is similar to real-world classes. The author pulled a bunch of images of classes from the internet, like what we have here, and wrote an algorithm to transform them into the classes frame that are used for adversarial training. And after pre-training, we can see that the generator will generate result like what we have on the left and in correspond to the real result on the right. Notice that these are pre-training results that are not targeted to any networks. Those results are later used in iterative training and run gradients into the targeted networks. Here are the evaluation on the digital attack. Those attacks are on the digital images, not the photo taken by the physical glasses. We can see that in this chart, the author used two models. The first is called Viral Geometric Group, which is VGG, and the second is Open Faces OF. And for both model, the author trained two submodels, one smaller one and one bigger one. The smaller one use less weights, and bigger one use more weights. As we can see, the AGN approach performs pretty well on both models with very high accuracy and with very high success rate of success. And the projected gradient descent model and the CCS16, which is a approach that the author used in the previous papers, are kind of varied in their performance. it worth noticing that the author also developed a detector um, that is that is theoretically able to detect adversarial images out of the out of photos. Um, the big idea behind it is that the whole fundamental of creating adversarial images that the images are not from the distribution of the original data. So technically, it is possible for us to check the distribution of the benign data and use that statistically find out that the generated adversarial mask is not in the sample space. However, because of the nature of AGN, the detector within the AGN model is able to defeat this detector that was proved to work in other papers. You can see the detail within this paper showed here. So after the success in the digital domain, they also work towards to the physical domain. Before start printing the glasses, they also make a bunch of optimizations over the model. The first one is they also train over multiple images instead of just one. Because in physical space, people might face camera in different directions. So if we just train it with one image, there is possible that the position of people will be different when we're really taking photos and cause the lower success rate. And the second is they also printed a 3D printed tracker glass that the attacker wear to take the photos. And the generator will attach the generated glasses exactly on the tracker glass. So it will produce the most accurate image of people that are really wearing the glasses during training. And the third is that the author also model the effect of light and illumination. The fourth is they also have AGN network to produce only the colors that the printers are able to print. And the fifth is that the author ensure that the transition between neighboring pixels are smooth, like there won't be two totally different pixels right next to each other. The attack is very promising in the physical world, as you can see those examples that I have mentioned before. So this chart is a more empirical evaluation of the results. On the left side, it shows the dodging results, which we can see that the AGN almost outperforms all of other models with very high success rate. And on the right side is impersonation results. As we can see, in this chart, the AGN model only used a few attempts to defeat the facial recognition softwares. So the author then developed a model to find out which aspect of the photo in physical world affects the success rate of the attack most. It worth mentioning that the illumination doesn't have a lot of effect on the attack model. However, the position of people have a much higher effect. And for VGG, if people change their position too much, the success rate will lower. But for open face, a few change of position won't affect the success rate. It's actually could make the success rate higher. Then the author proves that for the dodging attacks, previously there's only one attacker, and the attacker is training AGN on only this one person. However, the author proves that there's a way for AGN to be trained so that one same glasses can be applied on multiple people, and all of them can have this effect of the dodging attacks. The author used multiple, as we can see, the author how author do this is that while training AGN, not only use one image of attacker, the author use multiple attackers, and as we can see, the more subjects we have, the higher of possibility of success success dodging. And the different color bar is the number of glasses tried in each scenario. Like for this one, the author generate 10 glasses, and at least one of them is success. After that, the author tried to prove that the glasses generated are inconspicuous and look similar to real glasses. The author achieved this by recruiting about 300 participants and give them real glasses, AGN digital glasses, or AGN physical glasses. The baseline is 61%, which is not very high. But we can see all AGNs have 47%, which is a bit lower than baseline. And AGN digital, in general, AGN generated glasses have much higher rate than what the author have in previous works, which means the pre-training part mentioned before is working and are producing glasses that are similar to real glasses. It's also worth noticing that for digital dodging, on a single attacker, is more inconspicuous than universal dodging across multiple subjects. So this brings the end of generating glasses. They also then use the same model on digit classifiers and proves that the same model is transferable to other models. In this case, it's handwriting digits. So on the left side is original digits, and in the middle is a pre-trained generator. And on the right side is adversarial examples that is able to defeat the handwriting digit generator. Thank you.